Die kan, ja. Moet deze denk ik dan nog even doen, toch? Well, thank you for showing up, or at least checking your email in this room. Yeah, sure. Okay. So, who in this room has said this before? Yeah, I know a couple of those up there. Who also has a AWS bill? Oh, has said this about this AWS bill, insert cloud here. I definitely have, and I've also said the first thing. Followed by, I have no idea where that $17 comes from. It's been there since forever. Followed by the magic words, meh. Of course, it's going to be a lot of people in this room, I know. And that's because we never told anybody, well, not in these modern times, is trust but verify. Right? Can we actually, do we understand what's running in our infrastructure, our little cloud? Trust but verify is a principle. We'll tell most of our developers, filter input, escape output, or the other way around, I'm never sure. But we should, also in the infrastructure space, we should make sure that what we build is actually, we know what's running at any given time. If only that we know where our possible attack vectors are. Because if I were a hacker, I wouldn't try and hack the front facing interface for a bank or Netflix or wherever. I would try and find those, scratched one-time VMs, password hello world, for companies that basically have no network segregation. So that's the unpatched node that we're looking for, and that's more common than you would think. And to understand why, we need to understand the how, or the reverse. Back in the days when ITIL was strong, we used to have something called a CMDB, a configuration management database. It's completely different from what we think it is. Back in those days, we believed that if you turn something into an Excel sheet, we would live happy lives and the yin and yang would be in balance. Of course, they weren't. They never were. Because as engineers, we had many reasons not to do stuff. One, because we're lazy. Most of these CMDBs are incredibly complex to understand, let alone administrate. A node called a CI or a configuration unit thing. Okay, I'll continue while they restart the stream. Okay, cool. So back in the days of grumpy engineers in basements that run server farms, they were told everything needed to be in the CMDB. Their life wouldn't change whether or not the CMDB was up to date. It took a long time to actually do it. I've worked as a consultant in places where it took dedicated staff to understand how to update the CMDB, with the result being that nodes that were correctly identified as a production system took an extra step to get root access or sudo powers for when an incident was happening. So the aim of the game was to keep a system on a staging identifier for as long as possible, because then we wouldn't have to call the NOC in the middle of the night and explain to someone that wasn't an SME on my systems why I would have to have access to my systems. So the result was gamification and make sure that the system is not registered correctly. Those systems were, well, those were in the days before APIs, before automation, so there was also very manual to update. And it's, you know, we're all lazy probably, or we should be lazy, that's why we automate things. So when you couldn't automate it, you basically ignored it for the whole year. You took inventory for one day, made sure you made the correct mistakes, and then ignored it for an entire year. And that sort of made us as an industry allergic to CMDBs, right? They had no purpose, or they were wrong on purpose. And those are the people now that the gray-bearded, grumpy guys that basically say, don't do it. There's no reason. So there's an entire new generation that has no idea that there is some benefit to registering your systems correctly, if only for cost. So before I completely lose you, let's pretend we're some data science and we're going to do some data science on our infrastructure. So a data science pipeline usually contains 3 steps. It's extract, so we're going to look for where the data might be that we're interested in. We're going to transform it a little bit, and then we're going to load it or store it so we can actually review it for later time. Like these systems don't need to be complex. Here's on screen, there's a couple of ways to actually find out from your, let's call it Pulumi, open tofu code. I'll still need to replace that one. Like you can actually directly ask your Terraform code, your Terraform state, like how many things should be there. Simple JQ query, or in Bash, as the previous speaker was a big fan of. Like Bash is all you need for most of the stuff. Set, grep, did a bit of awk. You can find the amount of compute resources that are currently modeled in your code. And then you can go to the bill of your cloud provider and go, I find 90 nodes in my Terraform code. Are there 90 nodes on the bill? There probably aren't. So that's your first clue. The people that raise their hands on like how many nodes if it isn't in code, it doesn't exist. Most config management systems, like for instance Puppet, where you can see here on the screen, there's a sort of an inventory service that will have a list of things that have been registered to Puppet. In this case, there'll be 100 production servers I have since this morning. So those are, I know they're in my system, there are 100 nodes that are correctly configured, or hopefully correctly configured, but at least they call into Puppet every half hour and ask what's the correct configuration is. So that's my benchmark. I have 100 systems that are up to date, that are correctly registered, and now I need to find the outliers. Systems need to be registered in a couple of systems, right? One's your config management, the other one is your monitoring system, because you need to be able to find it. In this case, I'm just looking up, give me the sum of all the nodes that have a node exporter registered, which is, in our case, is one of the earliest things we install. That's one of the most basic metrics, exporters that we'll have on the system. So it's going to be everywhere. Every system, one of my systems will always going to have a node exporter. So for the people that haven't fallen asleep yet, 103 in Prometheus, 100 in Puppet. So I should really come to this talk. So now we all know what I'll be doing tomorrow. It's finding or hunting down those 3 nodes that do produce metrics somehow, but it wasn't registered correctly. The other one I came across the other week, I have roughly 100 nodes. There's another 60 in my staging environment. I had 1,900 DNS entries in our system. That was a big eye-opener. That was very scary. We had similar numbers in our IPAM system, so our IP registration system. So now I had to account for 1,700, so roughly more than 95% of my DNS entries, my IP entries, were not in active use, maybe. So our CISO definitely had kittens that day when we told them. Since DNS is one of those systems you need to be registered in to do things, I mean, you can't get around it, but that's usually what people do. They'll have a vanity URL and go, this is how we're going to reach my system. So DNS, IPAM, that's definitely something you're going to want to look at. One that I've also found interesting is have a look at your Jenkins, your GitHub Actions, and count the nodes you're actually deploying to. I have seen entire cube clusters that nobody knew about, but they were available in CI. Also, you're going to have a look at your vendor billing changes. That some of them are better than others. There's an example of AWS. They had a very, very good cost explorer. And then you can pretty much compare any variable you come up with against any other variables. The one with AWS is most of the time, they have many, many regions. And you're probably only going to deploy into 1 or 2 or 3, a handful, a known list of regions. And I've been at one customer where they had $2,000 worth of costs in a region that they definitely weren't using. And even then the answer was, meh. You know, our bill is whatever it was, I think north of 60K, so the 2K we don't particularly care about. And that was a financial institution that was controlled by quite a bit of legislation. The other one I'm going to mention here is the lack of signal is definitely a signal. So keep an eye out on team reports, or even news flashes that get sent around. Like, this new cool system X is just being launched, and you don't see your cost go up. So that basically means someone's having a skunkworks project somewhere in a cupboard. Signal is spelled, no? Signal, yeah, second signal is spelled wrong, sorry. So the lack of signal is definitely a signal. So keep your ear out, do some social engineering, and keep track of what projects are currently running and whether you believe that should increase the infra costs. And if it doesn't, then something is definitely up. Which means potentially there's unprotected systems somewhere in your that will have access to things they shouldn't have. I know here at Config Management Camp this might be a controversial statement. You're going to be big friends with the UIs that vendors provide, the suppliers provide their billing pages. In case our DNS provider, an external DNS provider, when I logged in, it was clearly shown that you have 1,900 or 1,800 DNS entries. If I had logged in at that website earlier, I would have seen that. but I didn't because I terraform everything because I'm lazy. But sometimes you just need to log into these things, and some of the metrics, the signals you're looking for is actually very clearly shown on these websites. So I can highly recommend just having a look and see what is available to you. Because there you can also start doing comparisons, SKUs, which is types of machines. So the SKUs that are applied, I think our Terraform code in our Terraform code we make sure we only use a certain type of AWS machine. And on my build, there's 3 different types. That's also a signal that someone is actually spending money or doing things they shouldn't. And as I mentioned, the cloud regions in AWS being the biggest offender. I know I only have 3 regions defined in my Terraform files, and there's 7 on the bill. So definitely those 4 other regions are now suspect, and something we'll need to deal with it. The metric system, that's the other one. You can ask all modern observability tools that I know of actually have metrics about themselves. So they all can actually tell you, you have 500,000 metric series in your system. Yesterday there were 400,000, so something showed up yesterday that is now producing 100,000 data series. Data series, if you use a SaaS product, in my case 400 to 500 means my cloud, in this case Grafana cloud bill is going to go up 20%. That's painful if we hadn't budgeted for it. It might also be an actual signal that there are systems that's producing something that shouldn't be there. In this case, I know it's new nodes that I deployed. I've seen these peaks before, and there was someone turning production, the debug mode on for the production, and then going to bed. Meaning that they produced, sorry, the maths escaped me, but when I turned it off, basically we had 1% of the data stream left. So they produced 99% overhead on their stream for a weekend, because of course they went to bed on a Friday night, as you do, and come back. And when I showed up on Monday morning European time, I had a huge peak that scared quite a few people. And then, of course, is the question: how crazy should I go automating this? Because we're all engineers, so it's all kind of data that we need to collect. You probably don't have to start. You know, try and work out a system where you peel off the highest value layer. So most of the time, you can just simply start with the bash examples I showed. How many nodes should there be? How many nodes are on the bill? Boom. Automation done. I've seen people go completely crazy where they start scraping APIs. Once APIs aren't available, you know, we'll mock something that clicks buttons for us. No, that's probably not what you need. Because it also needs to be in relationship actually to the $17. If you're really looking for cost, and $17 is, you know, a couple of minutes you're allowed to spend on it. If you ask the CISO, those going to give you a couple more hours to make sure it's actually the delta is actually safe. There's also tools that can actually help you basically turn everything into a SQL statement. Here's an example of something called Cloud Query. What they actually do, they wrap cloud vendor APIs into something that looks like SQL that you can then turn into a simple SQL statement that you can use in small code scripts, things that get turned into something that a human actually wants to read. Maybe an Excel sheet, because that's what CISOs, in my experience, CISOs seems to like. But it could be as simple as just your favorite SQL editor is going to show you a table. and then we can compare it to other tables with simple bash tools. But how about we're going to keep up with live? You know, we're all cloud native, so things that around the script are probably changing underneath me. So how we're going to actually fix this? So I've mostly been focusing on people doing naughty stuff. So if you want them to not do naughty stuff anymore, trying to work around the systems you have, is make it as simple as possible for them to do the right thing. One is actually at AWS, the example I've been hitting a lot today, is you can actually have a company-wide policy that says you'll only ever allow to deploy to EU Central 1, which I believe is Frankfurt, and then we'll add an organizational policy basically saying that's the one region you can go into. If there are still regions that have resources, don't apply this yet, because then you're not allowed to clean them up anymore. Or have another policy where you as an infra team actually have these powers still. That's probably, and then basically tag the shit out of everything, if it's possible with your vendor. You know, the 3-year-old at home draws on the wall, and that's basically what you need to do. You allow everybody to draw on the walls, tag their name on it, so you can actually find out every resource that doesn't have this tag is basically suspect. I mean, there's going to be people who's going to try and gamify this setup, but it's one of those things. So in open tool, you can actually set something called default tags. So we're going to, everything that we're going to build is going to have the following tags, and everything, we're going to have alerting somehow of that. If these tags are not present, you know, you're naughty, you're costing the company money, you're probably doing it off budget and unsafe. If you look back at your metric systems, you can actually force labels on things as well. Looking at Prometheus, you'll have a key value pair called external labels, and we can actually add these labels on it. This can also be gamified, but if you look at the example, we're actually reading the variables, the labels we want to set directly out of our Puppet certificate. For those people that don't know Puppet, Puppet has a server-client relationship that is secured by a certificate, which you're allowed to sign additional key value pairs into. And that's what I always do. Like the environment, production is always signed into their certificate, and that's the only one that I trust, because Puppet has the notion of facts, but facts are user mutatable. And the only thing that isn't mutatable if it's signed into their certificate. Another way for people to try to get around this is change this value, which I'm no longer allowing. Yeah. So this is the cop-out about containers. Containers are, especially systems in high flux. Supposedly that's what people mean when they say cloud native. Alert on things that cost you money. I've been at places where they said, oh, we just switched to a serverless framework. It's going to save us tons of money versus running containers on ourselves. What you need to know for functionless things is you pay per clock cycle, basically. They have in Amazon, for the longest time, they had a 5-minute limit on things that run fast. And it automatically would kill these things at the 5-minute point. This particular customer, their super fast functions ran 4 minutes 52, making it their system, their temporary functions basically ran 24/7. Compared to if they run it on a VM, it would have cost them 5,000% less. They didn't work that out until the first bill hit, which was huge. Like, whoa, how did that happen? How did we? Why did we not get notified? Because the average runtime was just below the 5 minutes. So they absolutely used everything that you could find in the system. And this is sort of the the painful truth at the end for people that have been ignoring CMDBs. Please use a CMDB, especially for more static things. It's going to make life a lot easier, where you can just query your system like a known system instead of having to cobble together the information. I'm going to introduce something called Netbox, which is, well, they don't call themselves a CMDB, they call them the source of truth. And why I'm introducing it? Because you can also terraform it. Or, so in this case, it's gonna, what I'm showing here is a 3-step process. One, I'm going to register an IP prefix or a CIDR. I'm going to read it out of Netbox again. And then I'm just going to ask Netbox, give me the first available IP in this range. Register it for, and then register it for me with the following DNS name. I mean, this is how lazy you can get with a system like with Terraform. Because it is Terraform, where you clean the node or destroy the node, all of this stuff goes away at the same time. So your accounting actually adds up in both columns now. Yeah, that doesn't sound very easy. Of course, in this ecosystem, we'll just have a module. So in our case, what we always do, we have a module that wraps a certain amount of steps. In this case, I'm going to create a server at supplier X, which is going to inject a certain amount of information they want to know, clouding variables, scripts, and then I'm just going to register it. And that's how you wrap it, and just tell everybody this is the module you need to have in your code. And in our case, we just wrap this again in a create node, or a supplier specific create node module, and then everything is taken care of for people that do their own, relatively own infrastructure. So we basically wrap this for them, making our admin a lot more accurate. That's the end. Any questions?
How can you handle like in cloud you use auto-scaling systems?
Yes.
That not obscure, but make the metrics a bit harder to monitor based on the metrics, because there may be skew, from static resources combined with like auto-scaling stuff.
Yes. So the question is, how do we take auto-scaling into account? That actually is the harder question. That's the same one as the Docker stuff. So it's, what do I do with volatile things, albeit machines in auto-scaling setups or containers? And it is, the answer is roughly similar. Make sure that you set same defaults on the module that wraps the auto-scaling settings. So have an upper limit that's not going to break the bank over the weekend. And you can also, most auto-scaling systems will emit some kind of metrics. So instead of looking at the metrics directly, you'll look at derived values. What is the rate of scale, or what is the surface below the curve for the people that did statistics? So you start looking at derived metrics like those, and be really careful, because auto-scaling is one of these things that is going to bankrupt you if you don't accurately look at it.
Any tips on resources that can't attribute, for example, API calls to something? For example, AWS has this kind of API calls that you can't attach tags to, but you see them in the build. And you only have like region and account.
Yeah, so the question is, how do I deal with resources that I can't particularly terraform, but happen to be API calls to whatever cloud provider API we have, and that one is harder and really dependent on the provider. What I've done before is basically try and set up a sort of a proxy and start counting there, if that is an option in the system. And that's how you do the double accounting. Like everybody needs to have a certain header, and everything that doesn't have a header, that will hopefully get you closer to where it's coming from. It's either a proxy before or after. And that's it.
XOS. Cool. Okay, so I'll start. So welcome to this talk about configuration management primitives. We're here at configuration management camp, but you also may know that it may also be called YAML camp sometimes because we end up doing a lot of YAML. But today I don't want to talk about YAML camp. I'll try to go a level deeper, and so I welcome you to check apply camp. We'll see what we mean by that. So what is check apply? Check apply is basically a function that looks like this. So here it's Python, but it will check the state of something. If it's okay, it will do nothing, and if it's not okay, it will fix it. And that's actually the basis of a lot of infrastructure automation tools. And it's really the building block that allows idempotency for stuff that is not made for it. As you can see, the state is a global variable, and that's really how it works. It's only side effects on a global variable. And it's pretty much what all software, automation software, is about when you look close enough. And in this talk, I'll try to talk about what's new in the check apply world, and we'll see if it's still relevant or if there are alternatives now. So briefly, I'm a system developer. I work at Rudder since 2015. I'm also a CF Engine contributor, and I used Ansible and Puppet over the years. So it's about configuration management primitives. I've talked about the check apply idea of checking if something is correct and fixing it only if necessary. But before digging into this topic, I want to start by talking a bit about the raw material that we actually manipulate when we are doing system automation. So what's actually the state we transform? So what's the raw material we use actually? So in our case, we don't use logs. It's mostly something we produce, but we don't use it. What do we use? Well, basically, software automation, system automation, infrastructure automation in general is made of some configuration data about the state you want your infrastructure to be in, and some APIs that you will use to apply this state. And in the middle, you have a kind of check apply somewhere. So we interact with system, what I call system APIs, which are kind of programming interfaces. Sometimes it's a big word for something that's really hacky, but it's actually a programming interface. And it's always kind of a high-level interface. The low level of infra automation is still very high level in the operating system world. System automation is really about glue and not deep actions. Configuration data itself can be either a program or a data or a declarative using a DSL. It doesn't really matter for today's talk because at the lowest level it doesn't change much. We have an expected state, we have a tool we can use which is a system API, and then in between we will apply the state to the system. It doesn't change much. So for the next slides we'll focus a bit more on the Linux context, Linux server context, and we'll see what system interface we actually use in automation on Linux systems. And for the most part, it's really something, it's Unix v7 actually, or stuff that existed there, or maybe something that we would actually call POSIX, but most of what we actually manage on the systems are actually using text interfaces, commands, maybe sometimes sockets, but that's pretty much all. So we still use kind of old interfaces. I've struck the C because using C APIs is difficult, so we often end up using commands and text interfaces for a lot of automation software. A bit has changed since the beginnings of, well, Unix 7 or even the beginnings of system automation. As systems have moved towards a more declarative type of data. For example, the init scripts were mostly replaced by systemd units, so we replaced the program by a data file. And most new server programs actually use data as source for their configuration, contrary to older software which often had a custom configuration language. So that makes system automation life a bit easier, but hasn't changed much apart from that. And we also have libraries like systemd, which allows interacting with the system in a more programming interface way and less hacky command parsing way. But yeah, all configuration management tools still run commands and parse the output using regexes to try to provide a nice interface for the users. It's the internals of automation software is often pretty messy. You'll see a nice, let's say, package management method in your configuration management tool. But if you look at the implementation, it will check the version of the package manager, and if it's Older than this version, it will add another specific option which is necessary, except if it's this exact version that had a bug that was not for which the fix was not backported to Rails, so we have to make a workaround. And automation code is full of workarounds, and usually pretty messy because of this very unprecise interfaces. And as an addition, the configuration surface of a modern Linux system is huge. It really looks like this. So, for example, if you just look at the runtime stuff, a Linux kernel has a lot of configurable stuff that you can modify at runtime. So, and there is state everywhere on the system. Every program that runs has its own internal state. So, the actual configuration surface of an operating system is really huge. So, configuration management generally only manages a very small part of it. So, you will install a few packages, you will configure a few files, and you will say, okay, my system is managed. And for the rest, I don't know, probably it's in the default state. So if I took my image from a cloud provider, it's in the default state that was used when creating the image. It may be a problem because we don't actually know the whole configuration of the systems, but only the small parts that we configure. And containers may look like a solution to this, but I don't think they really are, because we freeze the state of at least of the disk and the software, but we don't actually know what there's inside, and we still take things from outside and ignore almost everything, all the parts that we don't configure. And to conclude with this introduction, I will say that maybe configuration management has failed on some levels, because the immutable infrastructure software usually dropped everything configuration management that built and started over from shell scripts. Docker files are usually pretty ugly shell scripts. So why wasn't the software we built kept in this context? Well, maybe because it was not good enough, maybe because it didn't bring enough value, but maybe we can do better. And maybe there is still room for improvement. So now we'll have a look at the solution space. So how we actually do configuration management now and what we can do in the future. So what's configuration management? In the next slides, I'll describe it as an engine. So that's the core of the system that will read the expected configuration and apply it to the systems. And then you have resources which implement the different items you can configure, like packages, services, HTTP calls, anything. And we'll look more precisely at the resources level. And we'll see what are the choices we make when we implement resources now, what are the trade-offs, and what we can do better. So we'll start briefly with the engine. That's not the topic today, but that's the part of the application that will be generic over what we configure. It will just evaluate data, maybe make string substitution, iteration, and then call the resources with the parameters. It's kind of a big check apply with a structure that is often a stack, kind of a stack with some links maybe, with an exception that I know of, which is MGMT, which has a graph structure, which allows a lot of very interesting stuff. But for the most part, it's kind of a stack, so you take the first part of the policy, and then you take the first item in the first part, and then the second item, third item, and you will evaluate the policies like this. So let's start from our check apply. So that's still the same. And we'll see that we have a first choice to make, which is at which level we will make the limit between the engine and the resource. So does the resource decide on its own, or is the engine controlling everything? In this case, we let if we imagine that the check apply is implementing a resource, we give it quite a lot of room, because the resource is responsible for checking and applying, and make the decision between do I need to do something or not, and then doing it. But there's another way to do it. You could imagine that implementing a resource in your engine means implementing two functions, one check and one apply, and the engine is responsible for calling check, and then if it's not correct, calling apply. So that gives a very simple but first choice to make when you're designing the interface between configuration engine and the resources. We'll add another very simple feature, which is like dry run, audit, check. It has different names. It can be added really easily in a check apply function. You just add a new parameter, and then depending if your dry run value, your audit value is true or false, you will either, in case the system is not correct, you will either fail with an error or fix the system if it's not in dry run mode. So in this case, that's an additional parameter that the resource has to take into account. And it's pretty, it's implemented in most configuration management systems. Now we'll see something a bit more interesting that's not always implemented, which are all kinds of static checks. Because we can limit and precise what the resource expects. And it is in this example, I've added some switch to Rust. It doesn't change much. Add some braces, but it's also add some types in the function signature. And we can see that we take a directory resource. And in this case, we constrain the shape of what we take. That means that this resource will accept a path present, that means present or absent maybe, and a permissions structure that will contain, let's say, a Unix permission information. So in this case, we're able to know before calling it what the resource will expect, and we are able to validate the parameters and avoid calling it with invalid data. And that's something that not always present in most configuration management software. A lot of them will fail at runtime, and it may be interesting to try to catch errors before. That's what shifting problems left mean. That means getting the errors when you're building your policies and not when you're running them on production. Another important choice to make when you're implementing configuration resources is the return value, because you need some kind of a standard to be compatible, and so you require a kind of standard. So here is a very simple one, which matches the CF engine way, I would say, the original CF engine way with OK, repaired, and error states. And so when all your resources implement these three, one of these three outcomes, then the engine knows what happens and is able to react accordingly. Another question that is really interesting when designing resources is how far do we want to make things general? How far we want to have general interfaces? For example, do we want to try to make our resources multi-platform, or do we want very specific resources depending on the context? Do we want a package resource that will handle installing AUF packages using apt, DNF, or even an MSI on Windows, for example, or do we want very specific interfaces? And this is an important decision, because being too specific will mean that the software will become hard to use, because we'll need to think about the right resource to use. But being too general will mean that you will lack some precision, usually, and you will not find, for example, all the APT options. If you have a general package resource, then you probably won't implement all the very specific APT options. So there's a trade-off here that you need to find between a very general resource that would have thousands of parameters and would try to cover everything, and more specific ones. Another very important debate in the configuration management space, agent versus agentless. But in this case, what's actually the difference? Well, if we look close enough, when we are running our configuration management software, there is always a kind of agent, because there is a program running on the system and doing stuff. So, well, that's maybe a temporary agent, but there is kind of an agent. So this doesn't change much. Actually, if you want to make a system with an agent, agentless, there is a very simple option. You connect over SSH, you copy the agent, you run it, and you remove it afterwards. And it works really well, and it is even possible that some configuration management products actually added an agentless mode to their software by just doing this. And people are happy because they now have an agentless configuration management tool. I don't know if it's better, but, well, customers want it. But so at low level, there is really no difference for the resources. Whatever the process calling the resources runs just temporarily or for long periods of time. So this is not actually a decision, and we can have resources that work either on an agent or agentless, in an agentless context. Now we'll get back at the engine, and we'll see at which point we want the engine to be interleaved with the resources. Should our resources be pretty general, or should they share some state with the engine, for example, which would allow more features but blur the lines between the layers and maybe make things harder to debug and make it harder to have an interface that allows external contributors to build resources, for example. So there's also a trade-off to find here. And linked to this, there's a very interesting question, which is how are resources connected? Can a resource send information to another one? If you install a package with APT, can you send the version to another resource or something like this? This sharing of state is also an important decision. There are all other types of connection between resources. For example, some tools will make automatic grouping for example, if you have a policy that installs 4 packages, then it will group them and only make one call to the package resource with the name of the 4 packages. In this case, the engine actually merged the calls to the resource. So this is a way of connecting the resources, and that's an important stuff to think about when implementing resources. Another very classic one is to wonder if a resource can trigger something in another one. So if a package installation can trigger a service restart, for example, and how this works. How do the information goes from one layer to the other. And maybe the last one, but a very important one, is in which programming language will you implement the resources? Some software automation and configuration management tools policies are actually written in a programming language directly, and in this case you can just write everything, let's say, in Ruby. So you have the policies in Ruby, like in Chef, and you write your modules in Ruby. This is really good for like users that kind of like to write code, but we'll see that it also has some drawbacks. But it has a lot of flexibility because you can share information really easily between the resources and the engine. Or you can use a different programming language. So in case your software automation configuration management system uses a DSL or just a YAML data, for example, then you will need a language to implement the resources, which makes it harder to hack into the system, but also hides the complexity better. I'll continue with a side note about this programming language choice, because it's more important, even more important than it looks, I think. There are obviously some consequences, some technological consequences, some properties given by the programming language or the tech stack you will choose. For example, if you choose, let's say, to write C, it will be fast, it will be pretty portable, but it won't be beginner friendly. So you have some objective properties given by the tech stack, but there are also values and culture around the programming languages. And this will kind of attract different type of people. And so that's something you need to consider. Because it will participate in shaping the community. If we take a few examples of languages using in infrastructure software, we have obviously C for CF Engine in the 90s. Then we have Puppet and Chef in Ruby, Ansible and SoulStack in Python, more recent stuff in Go or C++ or Rust. And these are very different languages that attract different kind of people, maybe. So, for example, Ruby is something more oriented towards people who like to develop. That's not an easy language. That language focusing some aesthetic and some conciseness, while Python is maybe seen as more beginner-friendly. And so that maybe, I think a big part of the Ansible success is that it's really seen as something you can try to act on very easily with no prior knowledge. While, for example, in C, it's not the case, or even Ruby. And so this has an impact on your user base. If you have an automation software that requires development knowledge, then you will attract some SRE teams and people with this kind of background. But if you choose a simpler language or a data structure like YAML, then you may attract some more ops-oriented people who don't really like to develop. They may write some small Python scripts, but nothing more. So this will also shape the kind of community you will get. And in some cases, maybe a simpler, less powerful but simpler implementation can be easier because it will allow users to enter more easily. So that's really something to consider. What kind of people do you want to attract in your community? Do you want developers? Do you want system administrators who are not really used to developing with, let's say, object-oriented programming or functional programming or things like that? So that's something you need to consider, because if you write your software in Haskell, let's say, then that means your user won't be able to hack it. That may or may not be a problem. Now, let's say we don't want to write our own engine, because writing an engine it's really hard. And let's say we want to just create a resource to manage something for an engine we already have. And in this case, we can, the different configuration management tools have different interfaces to extend the resources you can use. So there are extension APIs. Sometimes there are two versions. One that you can use through a programming language, so a programming interface, and one with a simple data version, often with less features. So for example, for Ansible, you have a library, a Python library if you want to implement a module in Python, or you can just implement a module in any language with just JSON data. CF Engine also now has this kind of interface with basically a JSON protocol. So if you want to add a new resource type to CF Engine, you don't have to write C code with a very intricate interface, but you can write in any language and implement a simple interface. Here is an example of a call to apply something through a custom resource. So this is what is sent to the binary that implements the resource type. Okay, and it looks like this in the policies. So it's used just like a native. It's called promise type in CF Engine, but it's your custom type that you have implemented. Before getting more into the details of what we did in Rudder, I'll just give a few interesting facts about other configuration management tools that I find interesting. So let's start with MGMT. So this is the resource interface for MGMT, and it has a lot of interesting stuff, but one of them is the watch method, because that's really the core of the magic features of MGMT. Is that the resources are able to emit events that will be handled by the engine and will lead to immediate reaction when something happens to the resource. So let's say you have a resource which is a file, then it will listen to events through iNotify, and if something happens, it will send a notification and the engine will be able to react. So this is an example of a very specific feature that allows very interesting stuff. I'll talk very briefly about Jet. Jet it's now abandoned, but it was an attempt last year to build something like Ansible, but in Rust with more speed and reliability. One of the interesting choices it had was that the Unix shell, was the Unix system interface used to configure stuff. So it was an agentless tool that would connect through SSH and run commands. And that was the only way to interact with the systems. So I find it quite interesting, given the evolution of configuration management tool, that we are still getting back to basically Unix shell. DSC on Windows. DSC 3.0 is currently in alpha. It means desired state configuration. It's a configuration management tool built into Windows. And the new version is actually way more like our usual Puppet, Rudder, or others, because it's now multi-platform, open source, and resources can be written in any language. It's YAML based, so they are really getting into the configuration management that existed 10 years ago on Linux, but that's interesting to see. So what are we missing with all the current abilities that we have? Well, I think there's a problem with observability. The complexity grows, and we still get information about what happens in the configuration management tools through text logs, and it's really hard to get more information from these logs. They were made for debugging, to help system administrators debug the problems, But if you have a more global view and you want to see what happens on the infrastructure, then they're not really suitable, and you would need more structure output. And that's actually the hardest part when you implement a resource. If, let's say you implement an APT resource, that's not that hard, you just call a command. But then you need to handle all the failure modes, and you need to extract the information and return it in a structured way if you want people to be able to do things with it. And that's really what's hard in implementing a resource. There is also a problem of security, traceability. In the context of supply chain security threats, we really want to know what happens on the systems. For example, if we fix the permissions of a file, we really want to know what were the permissions before we fix them in a structured way that we can integrate, and not just in a human readable log file, because it's really hard to consume in, let's say, security grade tooling. So this is also important in security context to get better observability. Yeah. So some might think that immutability can be a solution to these problems. But the thing is, immutability is a model which has obvious qualities. But immutable does not improve observability magically, because immutable means frozen, but that does not mean we really understand what's going on. So it does not always help in this regard. And mutability also has some qualities. It's often faster, it's lighter. And if we make a parallel with programming languages, a lot of programming languages actually try to prevent mutability, to prevent all the bugs related to mutability. For example, a lot of functional programming languages did that. But it may not be the only way to handle mutability correctly. And for example, Rust aims at managing mutability instead of preventing it, because at the level of system software, we actually need something efficient, and we actually need mutability. And I think in some configuration management context, mutability can also be a quality and be something that we might want. So, in Rudder, now I will talk a bit more precisely about what we are currently doing in Rudder. So we have a Unix agent, which is actually a CF engine, an embedded CF engine agent. And we also have a custom Windows agent based on the native technologies like previous versions of DSC and PowerShell. And we want to be able to implement new resources, providing new features. We kind of believe in strong typing for Rudder in general, so we use Scala, Rust, Elm in the rest of the program. We look to keep some CF engine benefits like the performance and reliability. Our users, because of the way Rudder works, are usually not dev-oriented. They're mostly really ops, like people who want to manage system but not write too much software. So having a language that is accessible is not something we are focused on. And most importantly, we don't want a big bang. We want a slow transition towards these new features. So what did we choose? We chose to implement standalone resources, pluggable to our existing agents. We chose Rust as the implementation language because of these qualities of speed and reliability. And we obviously don't expect our ops users to write Rust, but that's not a problem. We might provide at some point a small Python API to do basic stuff, but our users actually want something that works. And we also have kind of simple resources for now, so nothing magic like MGMT. We mostly want to improve observability and security, and we don't want to provide like immediate reaction or event-based or nothing really magic like this. And so for this, we decided to use the extension interface of CF Engine that I presented just before, called custom promise types. This allows moving the complexity from the CF Engine DSL. We actually implemented a lot of resources-like stuff in CF Engine itself, but CF Engine is not suitable for programming. So this allows moving the complexity lower in the stack. And another interesting fact is that given the API is an arbitrary JSON, we are able to add another layer of abstraction between CF Engine and our resources, which allows these additional features. To make a small comparison, I don't know if you have heard about the Language Server Protocol, LSP, which is a standard for implementing IDE features for a language. So it comes from VS Code originally, but now it's present in almost all code editors or IDEs. And the principle is that you will, when you're writing a programming language, you will provide a binary that speaks standard API, which is JSON-based, and then any text editor will be able to plug to this, to call this binary and speak with it in JSON and get all IDE features like auto-completion, error detection, everything into your IDE with a single implementation, while before you had to implement it in every text editor. So that makes things easier for programming language authors. And I think it has kind of the same technical behavior. So that's an independent binary that just talks over std in, std out in JSON and allows plugging to different engines. So I think that's kind of an inspiration in our case, because we want to work with several different agents, but only implementing it once. So it works a bit like this. I don't think it will become a standard because the economy and incentives are a bit different. It's really hard to implement an LSP. It's kind of easy to implement a resource in general. And there are much fewer configuration management software than text editors. So probably, I don't expect it to become a standard, but I think it's still a good idea. And we actually have a Rust library that allows to build these binaries that implement the extensions API of, let's say, CF Engine, Ansible, DSC. And the same implementation could be used as a custom resource in all of these tools. It also includes some static validation and YAML data as input with some additional static verification, because we want to be able to verify things statically quite early. So this is what the interface looks like. You might not like the Rust syntax, that's not a problem. But basically, the first method is important. It returns basically the description of the interface. So it gives all the parameters, the accepted values, the documentation, everything. And then we basically have a check apply that takes some parameters to and return something which is either OK, repaired, or error. So that's a very simple interface, but it allows plugging to a lot of existing systems just with these simple methods. So that's currently exists and will be released later this year in Rudder. So we actually use this library, we implement the different methods, and then we build a binary that can be used by any of those of the agents. And the binary itself can output its spec as YAML. So this is quite flexible in its usage. Something I want to add at some point is some inventory features, because once we have this idea of centralizing, let's say, access to the package manager in one binary, then you may want to use it to get facts about your packages. So the inventory part could also come from this binary, and then the engine doesn't have to know anything about packages or services. And I would also like to add more structured output. Currently, it's only, given the constraints of CF engine and our existing Windows agent, it's only some text messages plus an outcome which is either OK, repaired, or error. But I really want to add more structure output, like diff if you modify the files, previous state of the resource when you modify something. There are some other perspectives in the check apply world. So we can think of NixOS, NixOps, Geeks, which are, NixOps is a configuration management software for NixOS, which are Linux distributions that have a very specific model where you actually describe the state of the system you want, and it will be applied by the system, and it will guarantee that the system is in the correct state by design. But it's a bit harder to use, and I'm not sure it will get to the server space. For now, it's mostly a desktop distribution. So it's interesting, but hard to use, so I don't know what it will become. And for making with another option is to make things easier to manage. So, for example, drop a Linux kernel and just build very specialized binaries with, let's say, microkernels, where the configuration surface is very small, so the management is easier. Or a specialized system, let's say like Talos Linux, which is a distribution that has a very limited configuration surface from the outside. There is no SSH access, only an HTTP API, but it's only for very specialized use cases of hosting containers. Okay, so thank you. That's the end of the presentation. What I want to tell you now is that I think there is really some things to discover in the configuration management space, that it's not dead, that it's not over, that not everything has been found yet. And there are a lot of new needs that we will have around security, compliance, observability, and that we really need some new ideas to be able to tackle them and have fun implementing stuff. I actually have a lot of fun implementing these resources. Thank you. Do you have questions? We have a bit of time, I think.
4 minutes.
Thank you. No? So thank you.
Which battery died?
Sorry?
Was that the battery that died?
Yes.
Okay, 25 minutes. So this will be a lightning tour then. Topic here is overcoming technical debt when moving to heterogeneous architecture. That means what are some of the common issues that you're going to encounter when you start to add some ARM64 to your existing x86 cloud infrastructure? Well, first question is, why would you even bother to do that, right? Why would you try? Why would you put yourself through all of the pain of adding a second hardware platform? Well, I'm hoping to convince you. This is going to be a little, it's not a sales pitch, but it's going to be a little bit less deep. Let me just put it this way. There is a philosophy difference between what the ARM64 servers are doing and what traditional x86 servers are doing. The first is we call ourselves Ampere Computing, we call ourselves a cloud native CPU. And what we mean by that is that it's built from the ground up for the needs of the cloud. So what does that mean? Well, we focus on single-threaded cores, very fast cores, right? These are 2.6 to 3 gigahertz. This is not slow cores, but single-threaded cores designed from the ground up for cloud-native workloads, right? Lots of cores per socket. And that matters because the industry continues to evaluate CPUs based on how fast a single core can go. That's what all the benchmarking tools evaluate, right? And yet, when you're deploying a cloud application to a cloud-native environment, when you're deploying a microservice application, you don't actually usually care how fast an individual core is. As long as it's fast enough, what you actually care about is how the workload behaves across a large number of cores. So basically, our argument is that the future needs of the cloud will be more cores, less power, more cores per rack. So in a 42U rack, instead of having, say, 18 or 20 servers, because you've got to leave extra space for cooling, for airflow, you're going to have the ability to go up to 38 servers plus a top rack switch. Which means it's good for your pocket, right? More CPU cores. If we're selling a CPU with more CPU cores and less volume, less power needs, that means the capital expenditure and operating expenditure for the cloud services go down, and therefore lower operating expenditure means that they can charge less per core hour to you as a consumer. Whether they do or not is another question, but they certainly have the ability. And we've seen in our CSP customers that their competitive pricing for ARM64 cores, and even more competitive when you think about, and we'll get to that a little bit later, when you think about price performance for a given SLA for your application. Finally, it's good for the planet, right? This is something that my colleague Aaron talked about yesterday. About 3% of energy production now goes to the cloud, and that's trending to, I really need to fix this typo, trending to 10% by 2033, according to one report that I read. And why does that matter? Well, it's kind of abstract. Like, one of the things that I found is cloud developers don't really think about the CO2 burden of their applications, right? But we're in a world now where there are zoning decisions that are being made around housing versus data centers in a lot of European cities, London, Amsterdam, Frankfurt, because of the demand that data centers put on the electricity grid. So in that world, we do really need to start asking ourselves, you know, this is a real estate question. This is a quality of life question for people who are living in these cities. Do we want more data centers or more housing for people? Okay, so I hope I've convinced you that it's worth looking at, but now the question is, well, how do you do it? And I'd say there's roughly a playbook that goes like this. It's you find out about the platform, you evaluate it for your workload, then you do your build, your test and optimize, make sure that your price performance and your performance profile is acceptable, and then move to deployment into production. So I'm going to focus most of this on what kind of issues you can hit between build and deploy. But basically, the starting point is when you're assessing, is look at what software you're running. Most modern operating system distributions, I mean, most cloud applications are on Linux. Most modern Linux distributions support ARM64 out of the box as a tier 1 platform. Because ARM64 is relatively new in the industry, like 5 years, you're probably going to get a faster experience with newer distributions like an Ubuntu 22.04 or a Red Hat 9 than you are with older versions like an Ubuntu 16.04 or a Red Hat 7. So all of the community-built distributions also typically support x86 and ARM64. And you certainly have your choice of commercial support if you want it. And then in compilers and runtimes, again, we've got that kind of need to go to newer runtimes. Java is one which I'll get into a little bit later, but there is so much Java 8 out there. How many people here have Java applications running on their infrastructure? And is it Java 8? Okay, Java 8 is like 11, 12 years old. So a lot of the performance improvements that have gone into the JVM have gone in between Java 14, Java 17, and even into Java 21 now. So you will get nothing by nothing but moving the JVM from Java 8 to Java 17, you get a 30% speed up for Java applications on ARM64, which is kind of wild. But obviously, ARM64, and I know everybody in this room knows this, ARM64 is a different architecture to x86. So you're going to need to recompile. Anything that's compiled code needs to be compiled to that architecture. For applications like Java, Python that compile to or Java or .NET that compile to intermediate language, or Python that's an interpreted language, you can just run your code. All of these runtimes, you know, they're fully supported on ARM, and as long as you stay in the mainstream, you're probably not going to have any issues. And then you got to think about what applications to run. So I will say one of the really, really key differentiators between ARM CPUs in the cloud and x86 CPUs in the cloud is the tail latencies that you will see on anything that's latency dependent, right? Video transcoding or voice or caching, for example, in-memory caching, are the types of applications where you see a massive improvement, not necessarily because of the performance of the cores, but because those applications, you care more about the worst performance than you do about the mean performance, right? So for example, if you're running an object cache as a service, you care about the experience that the slowest response will give a customer, right? You want to make sure that your tail latencies are as predictable as possible. And so one of the things that you see in the ARM64 architecture is that, and we'll talk about it a little bit later, is that you get linear scaling under load. So you can change your auto-scaling algorithm to, instead of scaling, adding new nodes at 65% or 60% load, you can go all the way up to 90% load before you add new nodes. Okay, but in general, the general rule of thumb is applications written with modern languages that are cloud-native scale-out workloads are going to be a super good fit for this platform. Okay, so I said this already. All binaries that you're going to run are going to need to be compiled for ARM64 natively or cross-compiled. So what does that look like? So let's take one example. It's going to depend on a variety of factors: the size of your application, the programming language you're using, and how much architecture-specific optimization is in your code. But if you look at something like Postgres, it is a single line, right? You add a -m CPU native, and then you build it. The makefile, it's going to work out of the box. That's not the typical experience. But you can certainly find a lot more transition and building guides on the Ampere Computing developer site. But let's look at some of the gotchas, some of the things that can come through that do make a difference when you're building. There are issues that will be revealed by the architecture change. And this is what I've been calling, in the title, that it often falls into paying down technical debt. And we're going to go through some of the gotchas that you might find. I've listed a few of them here, but I'll list them again later. Okay, first one, x86 specific C flags. If you have -m SSE2, for example, or any of the other x86 specific SIMD accelerators, right? That will not work on ARM64. You need to use the ARM64 equivalent, which requires recoding. But if you want to get it to work out of the box, you can just skip the SSE stuff and use the native CPU instead. Any C programmers here? Okay, there's at least 2 or 3 issues with this C code at the end. Yeah. Okay, so getChar returns an int. So what's going to happen if you have this code on x86? It's going to be fine, right? Because a char is a signed data type. It's a signed integer type on x86. However, on ARM64, a char is an unsigned data type. So this will never, this will be an infinite loop. Right? So these are the kind of things that pass through compilation that you come up with later. Again, I would call this technical debt. Okay, when you're doing cross-compilation, which is one way that people build their applications for ARM64, you have to really be careful of build caches. You can find yourself linking with x86 objects. These are all going to come up at compile time. They're not going to be deploy time issues. But you really need to make sure also that you're matching the versions of the runtimes on the target platform and the compile time libraries that you're using on the build platform. It's very, very common to have like version mismatches between kind of the libc that you're compiling on and the libc that you're going to run on, including, well, I'll get to that later. Again, ARM64 is still relatively new. Right, the Raspberry Pi 3 was the first 64-bit ARM processor, and the Raspberry Pi, that was 2016. I think that was really the point at which you started to see ARM64 become widely supported by open source projects. It entered into the server space in 2018 with Graviton 2. Then you have the Ampere Altra processor came out in May 2020. That's what's deployed in Google, Microsoft, Oracle Cloud. And then the Mac M1, November 21. So what you've seen is we've come into kind of general usage with Raspberry Pi, into the cloud with Graviton and Ampere, and into the desktop and high performance kind of personal computing with the Mac M1 and M2. What it means is that a lot of the improvements that have gone in to accelerate the performance of very commonly used projects, both in the cloud and in the desktop, a lot of those improvements have gone in since then, which means you need to make sure you're using a relatively recent programming language, operating system, and if you're deploying, for example, to Kubernetes, you're going to want to have a recent Kubernetes, Istio, and all the things. Okay, let's look at some gotchas that you can find in performance. This is going back to what I was saying earlier. All Ampere cores are real cores. There is no simultaneous multi-threading on Ampere cores, which means that when you get a vCPU from a cloud service provider, you're actually getting a core. You're actually getting a physical core. That has a big impact in terms of both resource isolation on level 2 and level 1 caches, but also in terms of the scalability of the processor. We also don't have opportunistic turbo frequencies. Don't ask me what that means. I just know that it means that we basically always run at the same frequency instead of modulating it. Here I'm outside my comfort zone. I'll just leave it at that. This, however, is the reason why what I said earlier about changing your auto-scaling algorithm is going to be so important. Apps will scale to higher loads. What you're seeing here is resource contention on x86, right? If you have two applications that are both going above 50% load on an x86 processor, you will see degradation and this will show up as degradation in the tail latencies for anything that's latency specific. You're just getting a little bit longer of a wait because you've got two things that are in a line and there's contention for the resource. So in terms of gotchas, you're going to want to update your auto-scaling algorithm and think about application SLA, not per core performance, when you're thinking about moving to ARM64. You can do the same work with fewer cores because you don't have that resource contention per core. So assumptions about the performance of applications and scaling behavior of applications are typically in cloud deployments are typically going to be based on a legacy view of the world, a world in which we have that one vCPU is equal to half of a core, and therefore you have resource contention. So let's talk about the deployment phase. The first thing you're going to have to do is you're going to have to create multi-architecture containers for all of your code. So I'm guessing everybody here knows what a multi-architecture container is, but can I have a show of hands? Okay, almost everyone. So a multi-architecture container is basically you build an x86 container, you build an ARM container, you put both of those on your container registry, and then you create a manifest which says if the container being requested is being requested on an x86 node, pull the x86 container. If it's being requested on ARM, pull the ARM container. And that manifest is then what is labeled with the general tag, whether that's a version or latest or whatever. So why is this important? It means that you can have the same exactly the same code for pulling the container on your x86 and on your ARM nodes. So this is going to require updating your infrastructure as code tools and all of your deployment pipelines to make sure that you're building your containers appropriately. Voila. The gotcha here is this is kind of a silly one. There is no standard across different hosts for what uname -m gives you in terms of the architecture. So you will see ARC64, ARM64, AMD64, x86-64, and x86_64, and it's going to be up to you to normalize to make sure that you get to the Go Arch standard, which is AMD64 and ARM64. So that's up to you. Also, very, very common problem is if you have anybody who can build containers and can upload those containers to your registry, at some point they will build an x86 container and overwrite your manifest. And what that means, has that happened to you? Yes. What that means is that if somebody on an ARM64 host pulls the container, it'll say there's I'm hesitating between it'll say there's no ARM64 container or that it'll try to pull the ARM container and run it and say, incompatible ELF format.
I can't say that was a while back, but
okay.
It wasn't fun to figure out that it was that because as you showed before, when you showed the details of it, differentiating AMD64 and ARM64 in that
yeah, you're going to laugh a little bit later. Okay, so more than one stalker pull fails because containers are given a tag that's an x86 container instead of a manifest. Okay, infrastructure as code, however, is mostly going to be straightforward. Most of the infrastructure as code tools are already multi-architecture. The main change you're going to have to do is to update your instance types and avoid any hard-coded either paths to binary files or like things that include an architecture tag. Avoid that in your infrastructure and as code in your Golden. Okay, so let's look at what's involved if you want to run a container application on Kubernetes. What's involved in adding an ARM64 node pool to an existing Kubernetes cluster and moving part of the application, because this is one of the things that's it's important to know. It's not an all or nothing proposition. You can move part of an application to ARM64 and leave the rest of your application on x86. Okay, so WordPress, everybody's favorite application. Somebody called it the poison of cloud native applications because, I don't know. recently, but I think WordPress is a fine application. It scales really well. Anyway, so we're going to start with basically this is a demo tutorial that you can see at the bottom here. If you want to go along and follow along, what we've got is a WordPress application using file storage, MySQL that's backed onto block storage. We've got primary and replica on the MySQLs, and then there's a load balancer, so you can have multiple application nodes if you want. There's going to be just one in the demo. So this is the Bitnami Helm chart for WordPress. It's nothing complicated. Okay, so the first thing you're going to want to do is you're going to want to go, this is on OCI, where you're going to want to go into, and there is no norm across different CSPs. You're going to want to go into the Kubernetes, either do this with the command line for the CSP, or go into the dashboard and add, you need to create an ARM64 node pool and add it to an existing Kubernetes cluster. And then there's the technique, the ARM64 primitives you're going to use are taints and tolerances. 5 minutes left. I'm nearly there. So you say basically, don't run this container on this type of node, or run this container on this type of node. And or you can say this container likes to run on this type of node with an affinity. And I think that's what we used. So you've got a Helm chart, you update it. So what we've done here is the MySQL database. We say, okay, this has a hard affinity for, and look, what you were saying, AMD64, ARM64, so it can run on either. What that does in practice is it runs one of the databases, the primary, I think, on AMD64, the replica on ARM64. And then we update the Helm chart again, and we run it again, and we say, okay, just remove the AMD64, the ARM64 becomes the primary, and all of a sudden we've got our MySQL is running on ARM64, and then we can update the Helm chart again and say, okay, now we're going to add a replica, but it's only going to use the ARM64. So you've basically, with modifying a Helm chart, running it a couple of times, you've moved your MySQL database. You have to give the replica process a little time to complete, but you've moved your MySQL database onto ARM64, so now you've got WordPress with part of your application running on one platform and part of your application running on another. Gotchas, sidecars. So if you use any sidecar containers, you're going to need to make sure that they are also multi-arch, otherwise you're going to be messed up. So remember, all containers deployed on ARM64 nodes must be ARM64 containers. If you are building, this is not going to be a problem for things like Envoy. But if you use a lot of sidecars, you're going to want to make sure that you avoid this. And, sir? I'm not speaking from experience, but AMD64 and ARM64 do look very similar. So you need to make sure that that might be the problem. Okay, so I'm going to summarize. I kind of flew through this, but our playbook for transitioning to Ampere Altra, ARM-based compute. Ampere is the processor for ARM instances on GCP, on Azure, on OCI. We're available as bare metal instances in Equinix and Hetzner, and that's about the end of my sales pitch. We have lots of information on our website where you can learn about the Ampere processor and deploying applications on it. Start by doing an assessment of your software stacks. Make sure that if you've got a lot of machine code in C, that's probably not a good place to start. But if you've got a Java application, oh, I forgot about my Java thing. Java 8. So this is one of the things that made Adam Jacob go, oh, why would anyone do that? Okay, if you're running Java 8 and you have to absolutely stay on Java 8, there is an option that will put the Java 17 JVM under a Java 8 JRE and fix all the plumbing. It's called the Enterprise Performance Pack from Oracle. So you can get Java 17 level performance with Java applications that are Java 8 applications. If you're stuck for some reason, I mean, I don't know why anyone would do that rather than pay down the technical debt and move to Java 17 or 21, but if you choose to do that, then that is an option. In your build chain, you are going to have to add ARM64 runners to any CI that you're using. That's a pretty straightforward and manual step. If you're using GitHub Actions, you can run self-hosted runners, and it works fine for private repos. It's not advised for public repos, just because people can clone your repo and run arbitrary code on your runners. ARM64 container images are readily available for most open source applications that you're going to come across in your cloud application. And there is a little bit of work to do to test and optimize to make sure that you're getting the right settings. And like I said, auto scaling algorithm, memory settings on Java and that kind of thing. But then you're mostly done. And I'm interested in hearing if any of you have a go and do well or have any issues. I am interested in hearing stories. I love those stories. And that's it. I'm done.
Thank you.
You're welcome. Was that high energy enough for the end of the day?
Yes, it was. But if you need some more energy,
Thank you.
here's a few.
Thank you. That was, well, there's another line I've corrected myself. In the past, I've said you can run ARM cores hotter than x86 cores, but I mean you can run them at a higher load. But that's obviously, they're not as hot. In fact, over the weekend, I was shown a 96-core ARM Ultra Max running a Kubernetes cluster. It was 3 control nodes that had 8 cores each, and then 32 compute nodes. So it was like, and it was pulling 14 watts, the CPU, while running a Kubernetes cluster. It was pretty wild. Anyway, so it is low power. Sorry.